Welcome to the talk about multi-connectivity in wireless networks. This work has been done together with Clara Steeghuis and Suzanne Bayan, and my name is Lotte Weedager. So I will tell you something about wireless networks, and in particular the network where users connect to base stations. In this picture, purple dots represent users, and users connect to their closest base station. However, in 5G, which is implemented in the coming years, it is possible to connect to multiple base stations. That's called multi-connectivity. And on the left you see two connectivity. So users connect to two base stations. And we are interested in, how useful is it to have multi-connectivity in your network? And we measure this with two measures. The first one is the channel capacity, which is a measure of the throughput or the rate of the internet that the user receives. And the second one is the outage probability. So what happens to the network if one base station, for example, burns down, or if a link breaks down. And those two measures will hopefully give an answer to the question, what is this benefit of multi-connectivity in the setting that we just described? And to elaborate a bit more on the setting, what we do is we have modeled this wireless network as two Poisson-point processes. So users are a Poisson-point process, and the base stations are also distributed by a Poisson-point process. And users connect to their closest two or k base stations. So if in this figure you see two connectivity, but it can also be 5. And then users connect to their closest 5 base stations. So the first measure that we're interested in, the channel capacity, is described as the Shannon channel capacity. You can see it's a measure of the bandwidth times the log of the signal to noise ratio. And this J is the jth base station. So a user, for example, connects to 2 base stations, and the closest one is then base station 1, and the second one is base station 2, etc., etc. So this bandwidth, we assume that is evenly divided among the whole network for base stations. And we're still interested in this SNR. I will come back later to that. And for the outage probability, we just use the probability that the user gets disconnected. So after some failures, that there is no connection left. We first zoom into this channel capacity. And we take the expected sum of the channel capacities. So if a user has 5 links, so if a user is connected to 5 base stations, we see that as the sum over those 5 channel capacities. And this sum of the channel capacities we can split up in 2 parts. We have the degree over which we need to say something, and this SNR. Well, as we use a size bias distribution, the degree is very easy to solve, but we have also written a different paper about that for the interested persons. So I will zoom into the log 1 plus SNR. So the signal to noise ratio is basically just inverse proportional to the distance of a user. So Rj is defined as the distance to base station J, where, J is 1, 2, 3, etc. And to cut it off, so the SNR bit doesn't become too large, we say that if the distance is smaller than 1, we just say that the SNR is C. And because we're using this Poisson-point process, we can say something about the distance to a certain base station. Namely, if J is 1, for example, so if we want to know if a user is the first, if a base station is first closest to a user, we want to know that in this circle around the user, there are no other base stations, where this is Rj. At the number of base stations in a certain area, the NBS is defined with this Poisson-point process, and therefore we have an expression for the distance, and thus an expression for the SNR. And this expression is plotted in this figure. And what you can see, which is interesting, is that for the fifth base station, so the fifth closest base station of a user, the SNR is much lower than the first base station. Which makes sense, since the distance, the expected distance to a base station 5 is larger than the expected distance to base station 1. So this is nice. We have found an expression for the SNR, and we can plug it in the expected log of the SNR. However, this is not a very easy expectation, as we could solve it numerically, but it became a very ugly expression. We also found a very nice approximation. So we just zoomed in on this part, so the expected log SNR, and we found an approximation for the high SNR regime. And the high SNR regime is basically a large C. So a large power and less noise. And what you can see is that we found a quite nice approximation, and also that for J, so the number of connections, it only decreases. And that also is our theorem that we concluded from this, that the channel capacity, the sum of the channel capacities, always decreases. So for larger values of multi-connectivity, larger degrees of multi-connectivity, the sum of the channel capacity always decreases, which means that multi-connectivity might not be beneficial if we look at the channel capacity. The second part we wanted to measure is the outage probabilities. And for that we designed 4 different failure models. As you can see here, but I will discuss them. So the first failure model was the random failure model, where just a link fails with a certain probability. So in this case, a quarter of the links fail randomly. The second one is the overload failure, where links fail with this probability, which is dependent on the degree of the base station. So in this case, the base station in the middle has a very high degree, and therefore all links connected to that base station fail. And then the third and the fourth one are based on distance. The distance failure, we say that after a certain distance, all links fail, so in this case 300 meters. And for the line of sight failure, we make the failure proportional to the distance. So larger distances have larger probabilities to fail. And in the coming figures I will show you what this means for the channel capacity and the outage probability. On the x-axis in this figures you see the probability that a link fails. So 1 means that all links fail and 0 means that no links fail. And what you can see is that, well, this confirms our theorem again, that the channel capacity decreases if K becomes larger. So if there are higher degrees of multi-connectivity. And of course, if all links fail, then there is no channel capacity. That makes sense. However, it's also interesting to see that this outage probability also decreases. So for larger degrees of multi-connectivity, so K is 5, the outage probability is much lower than for K is 1. This is also the case for the overload failure, where the links fail proportional to their degree, and also the case for the distance failure. And in all cases you can see that K is 1 has a much higher channel capacity, but that the outage probability is also higher for K is 1. Except for this one, since if all links fail after a certain distance, then also the second, the third and the fourth link will fail after that distance. So that is only dependent on the first base station. So that's, well, a nice result, and show that the channel capacity decreases for multi-connectivity while the reliability increases. If there are more links, it is less likely that you will have no links left after some failures. Something else that's very nice is that the channel capacity becomes more balanced amongst the users. And what I mean with balanced is that for KS1 in this figure, you can see that some users have very low channel capacity and some users have very high channel capacity. If you then look at KS5, this is less the case. So for KS5, it's more centered around 1 times 10 to the power 9. So all users have more or less the same amount of channel capacity and there are no large deviations in them.